Good evening. Welcome to another edition of The Laboratory. And we've had a pretty busy day here. Big squall line going through the southern plains, but surprisingly not seeing much on the SPC storm reports. There's one tornado report in Washington, of all places. Just some hail reports through Kansas, and everywhere else up and down the line in Arkansas down into Texas looks pretty quiet. But that's not to say we don't have quite a bit of convective action, and here's this big squall line through the northwest Arkansas area. This is about the strongest activity I can find this evening. And not really seeing anything particularly severe. These storms here are a little bit on the strong side, and this boils down to strong reflectivity gradients. So that's one little core technique you can use. And elsewhere, out here, you can see we're picking up some of the anvil that's being lofted eastward with a very strong upper air flow. Let's take a look down the line. We'll look at the Shreveport radar. And there it is, just a lot of disorganized storms, very forced appearance to this line from about El Dorado down to about Jacksonville. And then the line kind of tapers off into some discrete cells. But that's where we really have to be on guard, because these have not very much cell competition. So the potential there is a little bit higher for these storms to become severe. So I'm sure we'll be watching this going into the evening hours. Those are going to probably have a little bit of potential later on. And then further up the line where we had the hail reports in Kansas, here's the Topeka radar. And it looks like everything is kind of gelled into this cluster here, very, very large MCS. And I had my hands full today, so I wasn't really able to track these storms. But I saw about 20 or 30 hail reports in there. And here's what's causing it. This is the water vapor imagery. And you can see the main convective line from about Joplin all the way down to East Texas. And a pretty pronounced dry slot right in here. And this is actually kind of significant, because if you kind of take this away, take away the convective elements, you can kind of see how the dry slot covers this area right here. So that's actually a little bit of the EML, the elevated mix layer, that's riding on top of the tropical air. And that's kind of comprising some of the air that forms the cap there. Further back west, we get into more of the actual plateau air, the drier air. And then we've got this wrapped up low. This is basically the occlusion, because this system right here, this is getting cut off from the better baroclinicity out ahead of the system, and that's focused. I haven't looked at the charts, but I think we're going to find it maybe something like this here. Warm front up in possibly Illinois, and then a cold front down the line, or something like that. In any case, this is cut off from the moist sector. But looking like a bit of a hurricane there for sure. And this is the GOES-R imagery, the GOES-16 data. And there's a very close-up look at that little barotropic low in western Oklahoma. I'll see if I can load up a few frames so you can kind of see the rotation. I'm backing up in 5-minute increments. So this shows some of the cool capability of GO 16 right there. Let's see, I was trying to see if I could get this animating, but I don't think it's working out. But I can step through manually, and you can kind of see that rotating right there. So anyway, that's just some eye candy to look at there. Okay, for the big picture, let's bring up the thermal analysis. And before I get too much further, let me take a look at the chat, see what we got going on, and make sure the microphone's on. Sue M is here, and Andrew. Michael Burrell, 13, checking in. Fun with Tech, Ron Chalfant, Ahmed, Victor. David Holcomb says, enjoying the WeatherStar 4000 simulator. Yeah, that's a pretty neat. I don't know how many of you know about that, but there's a WeatherStar simulator where you can simulate the box that the Weather Channel was using about 10 or 20 years ago. I don't know about now. I don't have cable anymore or satellite, so I really don't know what the Weather Channel's doing, but it basically emulates all of the options, the forecast, the hourly weather, and it's just some neat stuff. Jeff Day is here. Alexi, Eddie, Adam, ASMR April, Jason Boggs, reporting from the Panhandle, says visibility yesterday was terrible with that dust there while trying to chase storms. And Mark is here. David Holcomb, Kevin McKinney, and got the whole gang here. So let's take a look at the fronts. You can kind of see that we've lost definition. We don't have the very tight gradient that we had yesterday. You remember in the Rockies we had quite a few contours. That's kind of, we've kind of lost that definition there. So we're going to be a little bit more dependent on the 850 charts and on the surface charts. But I can see a little bit of a gradient in here, maybe something like that. Nothing out really ahead of it, but yeah, up here, there's the warm front. So from Michigan to the Quad Cities and down to about Omaha. So probably looking at a configuration something like that, and then the occlusion all wrapped around in West Texas or western Oklahoma. Next system is coming onshore. There it is right there in the San Francisco area up near Marysville, northern California, and that'll be moving into the Texas area by Sunday. Let's take a look at some soundings. This is kind of a neat opportunity since we're right around that low pressure area. Fort Worth, where is that in relation to the system? Let's go back to the satellite, and at the time the Radio Sun was launched, they were going to be probably right in this area right here. So picking up a little bit of that dry slot. So what does the sounding look like? There it is, and showing a lot of dry air all up and down the column, and some very steep low-level lapse rates. And as I've pointed out, that's a good marker for modification of cold air masses. So probably the Pacific air mass may be undergoing a little bit of modification here. And it could also be just the mid-level cold temperature spilling out and then mixing down to the surface. And I think that's probably a little bit closer to the truth there. We've lost the moisture there at Fort Worth. You can see some very shallow dew points in the low 30s there, and then lower 20s and teens higher up in the column there. So severe weather potential in Dallas has pretty much shut down. Let's look at Oklahoma City. Oklahoma City is going to be a little bit closer to that low, kind of in these spiral bands. There's the Norman sounding right there, and dry in the low levels. Okay, so we've wrapped a lot of dry air down near the surface. Okay, that makes sense. But a lot of mid-level humidity. Probably a lot of mid-level convection going on there. And we can see an artifact here in the sounding. You see right here where the temperature goes up and then it goes very far over to the left. That's an artifact there. It's an error from evaporative cooling on the temperature sensor of that radiosonde. So that's one of the things you have to do, is be able to account for that. And the models even have to be able to pick up on that when that occurs. So these are some things that go on behind the scenes that we have to account for. And let's see, anything else I want to point out? Not really, just some very deep southerly flow there. And we'll try one more sounding. Let's maybe go up to Springfield, Missouri. And looks like they are contaminated. So that would be a radiosonde launch into a convective cloud. So we'll try Little Rock, and they're out ahead of the line here. And this gives us kind of a good picture what the instability profiles are like, because if we go back out to Little Rock, at the time of the radiosonde launch, which was about an hour ago, they were just ahead of this line. The radiosonde station is North Little Rock right there. So what does that environmental temperature sample look like? What does the moisture look like? Well, moisture is on the low side, not very rich. Looks like a lot of 50s dew points, up to about 6,000 feet or so. So if we mix that and clear this cap, not clear it all the way. I don't like to go all the way over to the right, but if we clear it where there's just a little bit of convective inhibition, looks like we got some mid-level instability here, some CAPE, and then some negative CAPE above that. So I think what's happening here is the dynamic cooling is moving in the mid-levels and the upper levels, and the column is actually cooling up at these levels. So the better CAPE is being realized out in the western part of the state. Okay, let's take a look at the dynamics real quick. And I don't want to bore you all to death, so I'll just kind of keep moving through here. There's the upper level low over western Oklahoma. Polar front jet wrapping around that. And it's becoming decoupled from the main band of westerlies way up in Canada. Okay, so what happens over the weekend? It just kind of shifts eastward a little bit. Moves into the Alabama, Georgia, Tennessee area. Here comes wave number 2. And wave number 3 is here. We've been talking about this the past few days. So as predicted, wave number 2 will be getting here on Sunday. And then wave number 3 showing up here around Wednesday or Thursday. And that'll be a deeper system affecting most of Texas. Then a little bit of a break, and it looks like we get this northwesterly flow system, and I don't remember seeing that in the model data last night. I think we were getting something from the west, if I remember correctly. So on the 1st or 2nd, we get our next wave, and that's kind of a northerly system, and then wave number 5, I guess, Okay, this one comes in from the southwest here. This is around April 4th or 5th. So a very busy pattern here, and I'm sure at some point we will see some widespread severe weather somewhere in the south or central U.S. here. Wanted to show you the 850 millibar cold front real quick, because we were talking about how the fronts did not have much definition on this thickness chart. So let's take a look at 850 and see if we have any help here. Okay, so there's the chart for this evening. And we can see that there's some warmer 850 air coming out of the deserts, and a bit of a temperature gradient from south to north, from about Abilene up to Amarillo. So I think the 850 millibar front with Canadian air to the north is kind of in this area right here, from about Wichita Falls to Abilene and back to Roswell. And we can definitely see the warm front. There's that front right there. That's the 850 warm front, and that kind of connects back into that low. And these are probably all wrapped up in the low, like what you saw there on the water vapor chart. And let's see what's going to happen real quick over the next 24 hours at 850. Looks like just warm air advection feeding up into the eastern quad of this low. So this is kind of a new warm sector forming up. Looks like maybe a little bit of a warm front frontogenesis in this area, and the new cold front coming down through the Mississippi Valley tomorrow afternoon, right about there. So those are just some things to look at with the upper level charts and the main barotropic low way back over Missouri right there. So maybe a chance for some cold core activity there in Missouri tomorrow. Those are always photogenic storms. Looks like that'll be moving up into Iowa on Sunday. So still maybe a chance for showers up in that direction there on Sunday. Okay, well, I thought we could take a look at a few SPC charts, since we have a few storms to look at. They're not the greatest storms. The Cape is on the low side, but we can kind of use this for practice, and this will come in handy as we get into more difficult forecasting situations. So anyway, you can tell we've got surface data, we've got winds, and we have radar. So what kind of radar data is that? Is that velocity? Is that spectrum width? Is that reflectivity? Well, obviously that's reflectivity, but the second question is that composite reflectivity, or is that base reflectivity? And there is a difference. Base reflectivity is what you're getting directly from the radar, such as this. You can see this is the Little Rock radar, and we're up at the 0.5 degree tilt. Yeah, you can see the options over here. We have the 0.5 selected. Okay, so this is basically just a scan half a degree above the ground. So when we hit the line here, we're up at about 8,000 to 10,000 feet. Now the other type of radar is composite reflectivity, and maybe to kind of show you this, I'm going to switch over to the Shreveport radar, where the line is not so messy. Okay, so there's the Shreveport convection on the base reflectivity. Now we're going to look at the composite reflectivity. And the question is, do they even offer it? I'm looking at their menu here, and I don't think they have it, but we can still get to it. We'll go to the Weather Service radar page. And I'll select Shreveport here. Okay, so I've brought up Shreveport. Let me drop the topography so it's a little bit easier to understand. Okay, so we're looking at base reflectivity. Okay, now I'm going to select composite. Okay, so you've seen probably a little bit of blooming going on. There's more echoes in this area right here. So I'll switch back and forth. There's base, and there's composite. Base and composite. So what's the difference there? Well, take a look at this anvil off in the distance. If I go to base, the anvil is not showing up, so it's not looking like this large blooming area, but on composite it definitely looks that way. This is because composite is looking at all the tilts at 0.5, 1.4, 2.4, all the way up, and it's finding the highest reflectivity in the vertical. So those have their different uses. Base reflectivity, looking at one tilt, that's better for analyzing your tornadic storms, looking for boundaries and so on. And I use that all the time, wherever I can. Composite is useful for some things. I find it most useful for when you're expecting convective initiation, when storms are about to fire. Those do not fire close to the ground. The first reflectivities are found about 15 to 20,000 feet above the ground, which means you're going to find it at higher tilts, like at 2.4, at 3.2, not necessarily at 0.5. So you can get kind of an early warning when storms are going up if you switch over to that composite and use that. And then when your storms are going, like what you see here, then kick over to base reflectivity. Okay, so those are just some tips on using the data. So what are we looking at here? That's actually a good question. They don't label it here. But I bet you, by the way, I would guess that the way this these echoes look, I think this is probably 1 kilometer reflectivity. Okay, let's. I'll bring up a few more products, and let me just take a look at the chat and see if anybody has questions so far. I guess this is turning into a little bit of a workshop, so I'm not going to make this too long, but we'll go over a few things while we have severe weather, or while we have thunderstorms out there. What cut off the ingredients today? I don't really understand the question. Cut off like by too far south, or the reason we don't have any severe weather? I think maybe Ryan's asking about why we don't have like a big outbreak of severe weather, and that's actually a very good question. And I'll switch over to a different chart to show you what's going on. Yeah, I've kind of missed covering the storm scale picture here. So let me bring up a few products here. We're looking at the high resolution rapid refresh model here. This is a convective model, which means it covers a lot of the storm scale physics, and it covers a lot of the processes that are out of hydrostatic balance. So in other words, it's very good at picking up on the dynamics that make up your small-scale systems, like what we see here. Okay, I've brought up the high-resolution rapid refresh radar, simulated radar. Now what I'm going to do is I'm going to click on the environment out ahead of this line. And you're going to see a sounding come up here. And I'll show you how to kind of quickly assess some of these parameters. Okay, I'm trying to get the window to fit here. All right, they've got a couple of parameters here. This is the effective layer STP. This is the significant tornado parameter. And this kind of quickly summarizes some of the key parameters that goes into a typical tornado outbreak. So if you look at this list here, we have CAPE, which is instability. We have LCL, which is kind of a function of moisture, a function of cloud height, of relative humidity. We have storm relative helicity, which is your turning of the winds in the lowest 1 to 2 kilometers, from the surface up to about 1 to 2 kilometers. And we have the bulk wind difference. So this is the bulk shear, and it's kind of a measure of your storm longevity. So if you have a downdraft that is separated well from the updraft and is not raining into it, then that updraft can keep going longer. And it's not going to get cut off by this downdraft coming down and raining into that updraft. And then there's this STPC, and to tell you the truth, I don't know whether I looked at the definition of STP to make sure that I wasn't missing something, and I really don't have any idea what this TPC is. This may be something special that they have set up on this website. But if we go through that list in different areas, and maybe I'll set this on Houston, because we were looking at storms in that area earlier, we can look at this and kind of see which ones stand out. And we can see here the CAPE is not shaded very much, so the CAPE is kind of low. And if we look on the sounding, yeah, the CAPE is kind of low. There's this parcel lift that's white. It outlines this CAPE here that's kind of long and skinny. Okay, so not a whole lot of instability. But the LCL is colored yellow, so we've got humidity, we've got shear, and we've definitely got bulk wind difference going for us. And yeah, we can see 70, 80 knot winds aloft. Let's check out what happens overnight. So I'm going to scroll this forward to about midnight. I'm going to set this on the Lake Charles area, and we'll take a look at those parameters. So we can see here the LCL is looking pretty good, so we've got good relative humidity. So very low cloud bases, that's going to be that's definitely associated with tornadogenesis. So if you have, I mean, of course, with shear and your instability, but if you have very high LCLs, if you have very high cloud bases and dry air, that's very detrimental to tornado formation. So those relative humidities look pretty high. The storm out of helicity looks kind of marginal. And if we look on the photograph there, yeah, this area is kind of swept out, but not by like a huge amount. And then bulk wind difference, it's got that kind of low. It's shaded in brown, and the value is down about 0.12. So that it implies weak winds. So I'm looking at this and I'm thinking, we don't have weak winds aloft. This is about 60 or 70 knots. But look down here. You got low-level winds that are about the same as what you have aloft. So the difference between the low-level winds and the upper-level winds is not very significant. So you don't have a very good bulk wind difference. Your bulk shear is kind of low. So that means that in spite of you having very strong winds aloft, the potential is there for you to rain into the updraft. So that means decreased storm longevity. So you can kind of use this. Again, this is on pivotalweather.com, and you click on the chart, and it comes up with a skew T, and you look at this box here. Sorry, it's off screen. Okay, there it is. So there's that box right there. I apologize. This may have been off screen. I'm trying to do this on two different monitors at the same time. But yeah, just look at this box here and kind of pay attention to the values. See which ones are high, see which ones are low. Match that up with your knowledge on using photographs, skew Ts, and so on. And this will kind of show you what's wrong with the environment or where things are good with the environment. Okay, so let's see here. What can we cover now? Let's look at a couple more products over at SPC. So this is at spc.noaa.gov/exper. There's some good products here to look at. On a day like today, we're probably going to be looking at mixed layer CAPE as being important for storm development. So this shows us where the best instability is. And we're looking at the values here in red. So values of 1,000 are kind of threshold values for strong thunderstorms, for severe thunderstorms. So the environment is only really supporting severe thunderstorms in this area. Looks like we've got problems up there in Arkansas. So values a lot lower. They're more on the order of about 400 to 500. Now, a lot of this is probably being impacted by all of the precip coming down here, all of the convective contamination. But if you look around the edges here, look at those values and look at the values here, that'll give you an idea of what kind of capes are feeding this cluster here. So I would say we're looking at capes of maybe about 500 there in Arkansas. So that's definitely on the low side. And that's the reason Arkansas is not really getting much severe weather, not much widespread severe weather. You can also look at most unstable. So this is another tool you can look at. And this is especially helpful for elevated storm situations, such as if you're north of a warm front. But you can use this in the warm sector too, and it's showing a similar picture here in this warm sector. 1,000 around East Texas, 500 in Arkansas, so basically the Cape is having trouble there. Now for tornado potential, here's one good thing we can look at. Go to this menu under thermodynamics, I'm sorry, not thermodynamics, wind shear. And go to the storm relative helicity, surface through 1 kilometer. Give me just a second, I'm going to use some throat spray, so My voice is kind of going out. Okay. Hopefully I got my voice back. Anyway, this is showing the SRH. And basically, values that are above 200 to 400 are conducive to rotating supercells. So when we're getting into these dark blue values, that's good for rotating storms. And if we kind of ignore the contamination we're getting, like back in here, I can see we're getting values of maybe 300 to 400 all up and down the line. So the SRH, the storm relative helicity, is actually fairly decent this evening. Cape is a big problem, but the low-level shear, I would say that that's there. Now, if we had a little bit more backing, if we had a mesolow developing, like if we had a mesolow form right there, back the winds out to the east in Arkansas, that would dramatically increase the storm relative helicity in that area right there. So it looks kind of homogeneous up and down the line, though, so I don't really see that happening here. Looks like just kind of a linear setup this evening. Okay, let me take a look at the chat real quick. I'm glad we haven't lost anybody. I'm always afraid I'm going to look over and see we've gone down to 15 people because I was boring people. But I'm trying to kind of like run through this very gradually and very consistently here and keep things going. So I'm reading the chat here. Calio Delphi says that storm system hit Fort Smith earlier tonight. Got some good rain there. Got some lovely mammatus over Fort Smith right now as the storm system moves on. Yeah, let's check out that radar. Okay, before I go up to Fort Smith, you can see that on the tail end of the line here, we've got more of a discrete appearance. And this has kind of a bow echo shape. So this is suggestive of high winds, locally strong winds right there, and we see the higher reflectivity gradients right there. So there's probably a little bit of severe weather potential right there, and this is right on I-20 around Marshall, Texas. So that's probably one storm to watch. This looks kind of like a lot of garbage here in southwestern Arkansas. Let's go up the line real quick. We'll go up to Fort Smith. And we can see that that looks pretty linear, looks very messy. But here again, there's a little bit of a bow echo appearance right there. So maybe a little bit of a localized enhancement of that cell right there. And there's a little bit of a discrete appearance right here. And by discrete, I mean kind of broken up into segments. So these are probably what I would keep an eye on right here. That's going to be south of I-40. I'm trying to remember what town that is, and I really don't know the towns in this area here. The rest of the line, this is mostly anvil. There's probably some good lightning in that, but this is mostly downdraft. And we'll pull up one more radar. Let's see. Let's go down to Houston, because there may be some potential there later tonight. You can see these are also kind of discrete, forming up into a little bit of a line here. But right now it doesn't look like any of them are severe. These here are probably a little bit on the strong side, but nothing severe there right now. Okay, taking a look at the chat here. David Holcomb is streaming WeatherStar 4000. Good deal. Sounds good. Yeah, after we close up, you can definitely head over to his channel and check that out. Every now and then when I'm bored, I'll run that sometimes. And in fact, I think I've got that on my channel here. If you dig down and look for WeatherStar, I think I've got a video in here of that. What's the data source we're seeing? I'm using weather.cod.edu, but I'm using a bunch of other sources too. I'm using meteostar.com. I'm using pivotalweather.com, and they've granted us special permission to use their images, and I appreciate that because they've certainly got some of the better imagery on the web. I'm using SPC, of course. There's SPC. And I'm using a few other bits and pieces like INCEP, National Centers for Environmental Prediction. That's where they run all the big forecast models. Okay, let's see here. Looking through chat real quick. When everything is present in the environment except for SRH, that is when the tornado forecaster needs to pay special attention to small features like outflow boundaries. Let's see, let me think about this. If you're lacking SRH, you're going to tend to get more splitting modes. So in other words, you're not going to have like a dominant right mover storm, that kind of thing. You're going to have storms that tend to go up and then they split. You have one cell that goes to the north or northeast, another goes to the southeast. And they tend to collide into each other, and if enough of that goes on, you tend to get a squall line forming from that. So that's one reason why poor SRH can be a problem. And in fact, I suspect we're setting up for something like that on okay, let me slow down here. April 2nd. Let me bring up that chart. April 2nd. Or let's see. Hang on a second. I'm on the wrong date. Okay, March 29th. That's the date I'm talking about right there. Okay, see here around March 29th, we've got this very deep system. There's a closed low over New Mexico. And we've got this very deep southerly flow in the mid-levels across Texas. And when I see this, I get kind of concerned that the atmosphere through a very deep layer is all out of the south. And what that means is you have a pretty good risk of having a unidirectional wind profile where a lot of the winds at all the levels are out of the south. And it becomes very hard to get storm relative helicity developing in that kind of environment. You have to have a very tightly concentrated mesolow, something to really focus the boundaries, that kind of thing. So this is probably a situation where we may get a squall line, splitting modes and squall lines in that kind of situation. And that's another reason why I don't really like these big closed lows moving in when I'm looking for like chaseable thunderstorms. I'm talking from the perspective of a tornado chaser. If you're wanting to see tornadic storms, you don't want to see these big low pressure areas because you tend to develop this unidirectional flow with that. We like to see more open waves like that right there. And we ran through a couple of case studies a couple nights ago. We were talking about Moore. We were talking about Greensburg, Kansas. All those were associated with waves like that. That's not to say you can't get severe weather with something like this, but you really need the right balance to really get a good severe weather outbreak going with something like that. And I think that did happen on the super outbreak of 1974, April 3rd. I think that was with a good deep low like that. So sometimes it does work out. Okay, that's probably about all we'll do for tonight because we're about 45 minutes in. Let me take one more look at the chat. A couple tornado warnings out for Shreveport. We'll take a look at that real quick before we sign off. Okay, there's Houston. I'm not too sure which one has a tornado warning on this. I'll probably have to look at the velocity. Then we'll go up to Shreveport. In fact, let me just use GR level 2, and you can see the warning right there. There's a tornado warning for Marshall, the Marshall area. So we're waiting for the data to come up here. While that comes up, I'll look at College of DuPage, and it looks like it is associated with that cell we were talking about. Remember we were talking about this bow appearance? It looks like we've probably got a bookend vortex on the north side here. And if you look up bookend vortex, you can find more information about these. And so basically what happens is when you get a bow echo like this that surges that way, you end up with a cyclonic vorticity pair here on the north side that will feed into your updraft and get wrapped up into the backside of the storm, and that can produce a tornado back there. Let me see if I've got this up. Yeah, there it is. So there's that vortex right there, just north of I-20, about 5 miles north of Marshall. Let me bring up the storm relative velocity. I'll run this back a couple frames. And that's probably what they were keying off of right there. You see kind of a couplet, a very tight couplet right there at Marshall. So this is a very tight circulation that looks to be probably a rotating wall cloud perhaps. Maybe a tornado on the ground. I don't know. I haven't looked at the warning. In fact, I could go ahead and do that. Radar indicated rotation. Okay, so yeah, this is probably just like a rotating wall cloud. We can see we've got 35 knots in towards the radar and 18 out, so that's about 55 knots of shear. So they probably saw that and looked at the potential there for a tornado right at that spot. So I put a dot right there. There's where that dot is right there. And then, of course, that's going to move out to the northeast. And it looks like that's probably kind of weakened a little bit. You can see as we advance that forward, you can see that circulation kind of breaks up right there. So it moves on up to the north, and I think they're probably safe up in this area now. I would say so. We can look at some mid-level rotation. I don't think I see any. Yeah, not really anything in the mid-levels. So I would say cautiously the coast is clear there. But of course, if you're in that area, take your precautions. Okay, so you guys can continue and check out some of that if you'd like on some of these sites, pivotalweather.com and SPC and so on. And of course, I believe one of our viewers there is going, I think Ryan is going to run that Weather Star thing after we close down. So I think that'll do it for tonight. I appreciate y'all watching, and maybe we'll see you tomorrow night. I will be taking a break either Sunday or on Saturday, one of the 2 nights, to hang out with family here. But I will let you all know what day that is when I know when it is. Anyway, thanks for joining, and we'll see you sometime over the weekend.